Afternoon, nerds. We're back to the OG sign, like I said.
It's good morning.
Is it good morning?
10:21.
Okay, you know what? Good morning. That's what I said yesterday on the sign, so today is good morning. Well, you know what? For all I know, you're watching this video at 2 in the morning. I could say
It's still good morning. I've done that.
Guten Mitternacht. It's German for good midnight. Okay, anyway, let's do this. We are continuing down the path of complex zeros of polynomials, okay? We have been given 3 zeros of this polynomial. X equals 1, x equals 1 plus 2i, x equals 1 minus I. Our job is to take these zeros, and maybe others, and come up with a polynomial function in standard form of minimum degree that has these as their zeros. A minimum degree means you don't have a reason to add more x's than is necessary. What was I not told that I know must be true, Nyla?
There's going to be like a positive and negative version of imaginary.
The word you're looking for is the conjugate. Yes. So both of these complex zeros require their conjugates to be present as well. It is impossible for a complex result to occur without its conjugate also occurring. They always happen in pairs. That means x equals 1 minus 2i, as well as x equals 1 plus I, are zeros. So then what is the degree of this polynomial, the minimum degree of this polynomial? 5, because you didn't see this one, Adi. But yeah, 5, because it has 1 real solution and 4 complex solutions. So we have a degree 5 polynomial. I'm not going to lie, this is tedious, but I need you to see it being done. What we don't want to do is we don't want to write this thing in its linear factorization. Where is it? Oh, it's right up above us. We don't want to have to do this and then try to distribute all that stuff out because it's not pretty. It's a lot of distributions. So many places where a negative sign could go wrong. So instead, we're going to do what I taught you yesterday, and that is how to rebuild the quadratic that produces complex conjugate results. And we're actually going to have to do that twice because I have 2 sets of complex conjugates. Just so you know, some vocabulary, and it would happen later on in the notes, but I might as well mention it now. A quadratic that doesn't factor to rational zeros, meaning whole numbers or pretty fractions like that terminate or repeat. Basically, any quadratic whose solutions are irrational or complex is called an irreducible quadratic factor. Just so you know, that's the vocabulary for that. So this is irreducible. I mean, we can get a linear factorization for it, they're just not pretty. We call those kinds of things irreducible. So we're actually going to produce 2 different irreducible quadratic factors of our 5th degree polynomial. We know that x equals 1 plus or minus 2i, and we also know that x equals 1 plus or minus I. I wrote 1 instead of I by accident. Whatever. We'll just make it 1i. I didn't need to write the 1. It was an accident. We're trying to rebuild the quadratic. And the plus or minus I, plus or minus 2i, both of those were a result of us taking the square root of a number. But the only reason why we would have taken a square root is if we were canceling a square. So what we're going to do is we're going to isolate the imaginary component, which requires us to subtract 1 from both sides in both cases. For the purple, we have x minus 1 equals plus or minus 2i. For the blue, I have x minus 1 equals plus or minus 1i. I'm just going to write I this time. I won't accidentally write the 1. And when you square an imaginary number, your result is always a real number. Always. Not a complex number. When you square an imaginary number. So if we square both sides, we will no longer have to deal with the imaginary component. I'm going to show this one off to the side because I need to save some vertical space. So I'm going to do this over here. This plus or minus 2i squared. It doesn't matter if it's positive or negative. When you square it, you're going to get a positive result, right? So it didn't matter if it was positive 2 squared or negative 2 squared. Either way, we were going to get 4. And then we have I squared. But I squared is negative 1. So right here, what I'm actually going to get is a negative 4. And that's why right here, I'm going to get a negative 1. Because this is going to give me positive I squared, which is negative 1. I've said this before, I'm going to say it again. I'm going to hope that because this is an AP course, you all know that this means x minus 1 times x minus 1, and you have the ability to distribute. Now we get our quadratics back to equaling 0. Because remember, you can't solve a quadratic in standard form unless it equals 0. So we're trying to undo all of that stuff to get us our two irreducible quadratic factors. We have x squared minus 2x plus 5 as a factor. And we have x squared minus 2x plus 1 as a factor. What did I write? Oh, plus 2. Sorry. Yeah, plus 2. There we go. There's a quadratic factor. There's a quadratic factor. And x equals 1 gives me a linear factor of x minus 1. Bless you? Was that a sneeze? No, bless you. Okay. And if we want this thing in standard form, all we have to do is distribute all this stuff. And I say it like it's fast and simple. Well, it is simple, but it's not fast. I have to distribute all 3 factors. I'm going to do it the same way that I showed you yesterday. I'm going to stack these things. No, just 2 of them. 2 of them at a time. Stack 2 of them at a time. And then you treat them like long numbers. 2 times 5 is 10. 2 times negative 2x is negative 4x. 2 times x squared is 2x squared. Negative 2x times 5 is negative 10x. Make sure your like terms line up. Negative 2x, positive 4x squared. Make sure your like terms line up. And negative 2x times x squared is negative 2x to the third. Okay, now take your x squared and distribute it. X squared times 5 is 5x squared, lining up like terms. X squared times negative 2x, negative 2x to the third again. X squared times x squared, x to the fourth. And just like you would have done with long numbers, you add straight down. Distributing vertically like this, I feel like is so much better. I don't have to track down my like terms. They're all just stacked nicely. I now have this 4th degree polynomial as a factor and this x minus 1 as a factor. So we're not finished until we distribute this x minus 1 to this thing. It is very tedious. Yes, that's why I say it's tedious. It's not very difficult. It's just a very lengthy process. And this is on your test. So guess which part of your test it will be on. Yeah, it'll be on the graphing calculator portion. You can't do it on the graphing calculator. Unfortunately, the graphing calculator does not have a computer algebra system in it, so it does not have the ability to multiply polynomials and give you back a polynomial. Well, not our calculator. Yes. Calculators with a computer algebra system can do it. TI Inspires, TI 89s. They cost more money, and you're not allowed to use them on the AP exam. Yes, Martin, what's up? Yes, the Inspire is allowed on the SAT, but that's because its computer algebra system doesn't really help you all that much. You ever wondered why the TI Inspire's keyboard isn't a QWERTY board, why it's in alphabetic order?
No.
You've never wondered why?
No, I have not, but now that you brought it up,
I mean, isn't it difficult to kind of find a letter? Because you're used to a keyboard, right? The reason why TI did that, why Texas Instruments did that, is because the SAT specifically says you cannot have a calculator with a QWERTY board on it. So Texas Instruments said, fine, we didn't put a QWERTY board on it. It's alphabetic order. So it's a loophole. It bypassed the rule. That's why it's like that. Isn't that funny? It really does. And you would think like alphabetical order in the language we speak, it would be easy. No, it's really difficult. Like, where is D again? Oh, that's right. It's after C. You know, it's tough. Yes, I know why QWERTY boards are the way they are. But let's get back to the math and I'll explain that later. Because I'm a nerd, that's why I know. Yes. So negative 1 times 10 is negative 10. Negative 1 times negative 14x is positive 14x. Negative 1 times 11x squared is negative 11x squared. Negative 1 times negative 4x squared cubed, positive 4x cubed. Psst, hey, pull yourselves together back there. And negative 1 times x to the fourth is negative x to the fourth. Now we're going to take this x and we're going to distribute it to everything. I have a 10x. I have a negative 14x squared. A positive 11x to the third. And a negative 4x to the fourth. Lastly, get skinny math, x times x to the fourth is x to the fifth. And we're going to add straight down. We're going to get f of x equals, adding straight down, I have x to the fifth, a negative 5x to the fourth, a positive 15x to the third. Why doesn't it want to draw on my fives? What's going on right now? Negative 25x squared. Good Lord, I'm going to run out of space anyway. I'm just going to wrap it around. Positive 25x, 24x, excuse me, I can add minus 10. Add straight down. And that's how we get our polynomial. So this is a fifth degree polynomial. It has 5 solutions and only one of them is real. It has 4 complex solutions. Wow. Okay, everybody's done now? We're done talking about anatomy and QWERTY board history and all that stuff? Yes? Okay, great. Next. This is another fifth degree polynomial. That means it has 5 linear factors. That doesn't mean all of its linear factors are pretty. Some of them could be irrational. Some of them could be complex. Some of them could be pretty and real and rational. We'll see. So the way that we have to approach this question is we have to grab our graphing calculator technology, and we are going to identify possible answers. He's still using. I've moved on. Pay attention. You're going to go to y equals, and you're going to graph the equation. You'll notice mine's already typed in. I'll give you a moment to type yours in. The reason why we're going to graph it is because we're looking for potential real solutions. Zoom 6, I'm already in the standard graphing window from earlier today, so I'm just going to hit graph. Obviously, this is the last thing I graphed, so we didn't get to see it draw the image, but there it is, and when you press graph, you also do the same. What we see here is potentially x equals negative 2, potentially x equals 1, potentially x equals 4. Now, for all we know, it's 3.99, but we see that it could be -2, we see that it could be 1, and we see that it could be 4. How are we going to test them? Well, how do we test a number to see if it's an actual solution? You plug it into the equation, and if you get 0, then you found a solution. It's basically using the remainder theorem. So what do we see? We see possibly x equals 1. These are our candidates. These are possible things. No, I don't. No, I wanted you to look. I wanted you to see that -2 was possible. I wanted you to see that +1 was possible. And I want you to see that 4 is possible. And then you'll use the remainder theorem, which essentially just means plug the solution in. And if you get a 0, there would have been no remainder. That means you found a solution. So we're going to see what is f of -2. We'll see what is f of 1. And we'll see what is f of 4. And because I don't feel like typing all that out, we're going to cheese this a little bit. And we're going to go to the table. Second graph button. And this is a table of values. Again, second graph will get us here. And then look at the y values when x is -2. Yay, it's 0. When x is 1, yay, it's 0. When x is 4, yay, it's 0. So yes, all three of those numbers are solutions. Now, I do want to point something out in case you've forgotten how to do it. What if, when you graphed it, you suspected a number like 1.5 was a solution? You see, this table currently only shows me integer values of x. But I can change that. Let's say I wanted to check a 1.5. Then I could go plus. And the reason why I'm hitting plus is because I'm reading the instructions on the screen. It says press the plus button for delta table. So plus. And now I could type a number. If I wanted to go by 0.5s, I could type 0.5 and hit enter. And now all my x's go by 0.5s. If you would like to go back to ones, hit plus, 1, enter. And it goes back to ones. Now you might have noticed somebody's calculator somewhere in the room, when they went back to ones, they might have noticed that everything said like 0.5, 1.5, 2.5, 3.5. Did that happen to anybody? Okay, can I see your calculator so I can show everybody how to fix it, including on the video? So here is why that happened. Actually, let me recreate the issue on my calculator. I'm going to go plus sign, 0.5s, hit enter. Now what happened was she scrolled to somewhere that had a 0.5 at the end of it. And then she hit plus sign and said go by ones now. So it went by ones starting from the number she had highlighted. So how do we fix that? You can go second window, which takes you to the table set, and tell it to start at 1. And then back to the table, and you're fixed. There you go. You're welcome. It was good to have on the video, so I'm glad it happened to somebody. Second table set, which is second window. I'm gonna tell it to start at 1. There. Everything's cool in the gang now, right? Okay, great. We are finished here. Boop. We found 3 solutions. That means we found 3 factors of our 5th degree polynomial. Right now, we know that x plus 2 is a factor because x equals -2 is a solution. We know x minus 1 is a factor because x equals +1 is a solution. And we know x minus 4 is a factor because x equals +4 is a solution. These 3 factors would multiply to give us a cubic factor of this. So we have some options. We could either perform division 3 times in a row to get to a quadratic. And the reason why I know it's a quadratic is because if you divide a 5th degree by a 3rd degree, because that's what this is going to create, you'll be left with a quadratic. Or we could figure out what this cubic is and just do long division one time with this cubic. That's what I'm going to do because I feel like it's less work. So I am going to distribute all of this. I'm going to multiply to get a cubic factor of my fifth degree polynomial. So I'll start with x plus 2 and x minus 1. I'll hope everybody in the room can distribute and get to x squared plus x minus 2. Then I'm going to take that x squared plus x minus 2 and I'm going to multiply it to x minus 4. Again, I'm going to hope that you can go through the distributions and combine your like terms. I see an x to the third. There's minus 4x squared plus x squared. There's minus 4x minus 2x. And there's plus 8. This cubic is a factor of our fifth degree polynomial. That means when I do long division, I'm going to get no remainder. What I will be left with is an irreducible quadratic. And how would we solve using Algebra 1 skills an irreducible quadratic? The quadratic formula will do it. Now, I believe we're going to get lucky and not even have to use the quadratic formula on this one. No, listen. We have to do the division first. After we do the division, any fifth degree polynomial divided by a third degree polynomial will leave a quadratic. And then you'll have your A, B, and C. Possibly. So let's do some long division here. Oh, by the way, when you do long division, just reminding you, you have to make sure that neither the dividend nor the divisor has any missing terms. 5, 4, 3, 2, 1, none. 3, 2, 1, none. We're in good shape. Nothing's missing anything. Sorry, my hand is always in the way when I'm writing. I forget to hold my pen at an angle so that it stays out of the way. Because I don't normally write like this. What's that? I mean, I didn't want to say it, but I was certainly thinking it loudly. Yeah. She said, at least I'm not left-handed. My best friend down at Northport, he keeps a box of pens that students could use whenever they need something to write, but he chooses who gets what, and he saves all the gooey ones for the left-handed kids just to mess with them. Yes, Adi, what's up? Yes, thank you. The good news is it only affects 11% of students, so 10%, something like that. 10 or 11%. Anyway, long division works like this. Remember, I need to make this x to the third become an x to the fifth. What am I going to multiply by? Is more than just Nyla here today? X squared would be great if lots of people knew that. I'm going to line up my like terms. You think it's x squared? Oh, that's good. All right, so I'm going to take this x squared, and I'm going to distribute it to this whole thing. It's going to give me an x to the fifth, 8 minus 3x to the fourth. That's interesting. Did I multiply wrong? No, I did it right. Okay. Minus 6x to the third plus 8x squared. Great. Time to subtract straight down. And the reason why I said it was interesting is because check this out. It takes out two of the terms. Remember when you do minus negative, it's actually plus. So I have 1 minus 1, 0. Negative 3 plus 3, 0. Negative 5 plus 6, that gives me a 1x to the third. Okay, so I have a 1x to the third. 5 minus 8 gives me negative 3. And typically you would just drop down this negative 6x, right? Oh, crap. I didn't mean to write it in green. Oh, well. It already happened. But you know what I'm seeing? Oh. You know what? I'm just going to bring down the 8 also because what would I have to multiply this by to get this? 1. Oh, there's our irreducible quadratic factor. And that's actually very easy to solve. X squared plus 1 equals 0 is really easy to solve. Yep. Subtract 1 from both sides. And then cancel your square with a square root. Just remember that anytime you cancel a square with a square root, it's going to produce a plus or a minus. And the square root of -1 is I. We now have our 5 solutions. -2, 1, 4, positive I, negative I. That means we know our 5 linear factors, which is what the question asked us to do. Trying to figure out what color to write in. I'm going to write the answer in green. Yes? Mm-hmm. Is there going to be a question like this where it has everything? What does that mean? You mean long division, complex roots, and all the remainder theorem and all that jazz? Yes. But it'll be on the extended response portion of the test. Like this? No, there's more than one question on their extended response. They have a part A, B, C, D, E. So I've held your hand through it. You got this. Anyway, f of x equals, order of multiplication is unimportant, so I could write my 5 factors in whatever order I want. So the first one we had x plus 2. Then we have x minus 1. We also have x minus 4. And then we have these two guys, x plus I, x minus I, and I throw in the nerds tag, and we call it a day. I know, I'm bringing panic. Nerd.